Thank you for coming for the Steve Saleeby seminar today. I'd like to little bit briefly introduce Steve Saleeby. He's a senior research associate in the Department of Atmospheric Science, Colorado State University. He received the bachelor degree in physics at the College of Charleston in South Carolina in 1997 and a master's degree in atmospheric science at the North Carolina State University in 2000. And soon after, he joined Colorado State University, where he has collaborated with the leading researchers such as Bill Cotton, who is a legend of atmospheric science, and Sue Van de Teever, who is the most active woman in the world. And his work focuses on the numerical modeling, cloud microphysics, and aerosols cloud interactions. And he has authored over 50 peer-reviewed publications. And also he serves as a lead developer of LAMS modeling right now. He is a co-lead of the model intercomparison project in the aerosol cloud precipitation and climate working group. And he is also working on the intercomparison project for the tracer, DOE-supported tracer field campaign. And then out of the research, he enjoys the distance learning and a wide range of outdoor activities from hiking to kayaking. And today he is talking about the aerosol impact on cloud microphysical properties in deep convection. Yeah, please take it away.
Thanks, Mariko. Is this turned on? Thank you, Mariko. Can you hear me in the back? Is this working? Okay, great. So thanks for inviting me here. It's great to be here. It's my first time in New York, actually. And so Mariko and I and Pavlos have been working on a joint project for proposal that we wrote a couple of years ago to the Department of Energy. And we're looking at aerosol impacts on microphysical processes and deep convection. So I'm going to present some of the observational work that Mariko is doing that we're writing up right now in the paper, and also talk a lot more heavily on some of the modeling work that we're doing that expands from the observational type work that we're doing so far. So just to give a little bit of background, this work really originates from this project, the Aerosol Cloud Precipitation and Climate Initiative that began about a dozen years ago. Mike Jensen at BNL and Sue Bannerheber were heavily involved in this, Pavlos as well, and some others. And they highlighted the need for improving our understanding of aerosol convective interactions in deep convection. So they initiated this model air comparison project using 8 different models and collaborators from around the world. And they focused on simulating aerosol convective interactions near Houston. And Houston was chosen because there's a ton of pollution there. It involves complex interplay of an urban area with a coastal zone, sea breeze effects, and there's a lot of summertime isolated convection that happens in the area. So that's kind of the idea for focusing on Houston. And a couple of key things that came out of this MIP is that we demonstrated that models display reasonably good agreement concerning aerosol impacts on cloud rain and warm phase microphysics. However, the MIP revealed that there's a lot more variability in the simulation of total ice and the mixed and cold phase cloud processes in deep convection in this region. So we're going to focus a lot on the cold and ice phase aspects today and what we're learning from observations and models studying convective cases from the DOE tracer field campaign in the Houston area. So that previous work kind of spearheaded efforts providing the motivation for the Tracking Aerosol Convection Interactions Experiment, or TRACER, that took place in the Houston area with the IOP in the summer of 2022. And so our contribution at CSU from this was running simulations for various cases that were observed during TRACER. So we've run 6 different TRACER case study days, and we're looking at idealized low and high aerosol concentrations that we apply to the simulations to explore aerosol indirect effects on the microphysical characteristics of deep convective cells in these simulations. And then on Mariko's side of things, we're looking at the CSAPR2 radar tracked cells and separating those into the best we can of low conditions and high aerosol conditions based on observations near the radar, and also to examine potential aerosol-induced differences in these observed cells. So we're coming at this from an observational and modeling perspective. Okay, so a little bit of background on tracer. I wanted to show some images regarding the area that we're looking at. So here is the Houston area focus for tracer. The main instrument site was at LaPorte, Texas. I believe this is, correct me, Mariko, but the CSAPR radar site was at Pearland. And so we're able to scan for the convection roughly in the Houston area. Here we can see the urban area of Houston and the dense haze layer introduced by all of the urban pollution. And then we can see a storm developing relative to the Houston area on another day at a time. So there's a lot of urban aerosols, a lot of potential convection in this region. And just a few other images here. We have a couple of cloud radar that was on site, some other instrument containers in the area. I believe this was the CSAPR2 radome in this area as well. This is a Tamanasuba and Changai Kwang from Brookhaven Lab working on some of the aerosol instrumentation. And then Mike Jensen and Changai in a deep philosophical discussion. So I was wondering what they're talking about here. And I'm pretty sure they're concerned that it's really hot and really humid. To be in the Houston area in the summer must have been brutal. So I was glad to be behind the screen, working on the model in an air-conditioned environment. And this was a photo from a meeting that we held. It's kind of a joint ACPC and Tracer meeting in 2023, held at Texas Southern University, where a lot of us from these two different organizations getting together to discuss some of the science coming out of Tracer, as well as how this fits into the ACPC initiatives. Captured, I don't think Mariko is here, but we've captured Pavlos over here. I'm back here in the back row. Danny Rosenfeld and Mike Jensen, who worked a lot on the ACPC and Tracer organizations. So it was a good meeting where we kind of discussed the first science coming out of Tracer. Okay, to go a little bit of background and what we're going to be looking at. What we're trying to simulate and trying to study is incredibly complex. So here's a figure from Hugh Morrison paper a few years ago, just demonstrating the complexity of what's going on in a deep convective cloud. And at the fundamental of all of this is the ingestion of CCN or INP particulate matter into the cloud. And once those get into the developing cloud, we start to get droplet activation and condensation onto these droplets. And this really starts the ball rolling. If you change the distribution of aerosols, you change the distribution of cloud droplets, that can affect everything that happens downstream. And so we want to start to try to understand this a little bit better from the observational and modeling perspective. So we'll look into some of the distributions of ice and some of the process rates that we can pull out of the model and try to disentangle some of these effects where changing the aerosols can change everything else. And this is just another image for a paper I wrote a number of years ago that shows the complexity of how we want to try to represent aerosols in the model. And it's incredibly complex. Some models do it at different levels of complexity, where we have to deal with aerosol activation, nucleation scavenging, fractional transfer of aerosol mass within the hydrometeors from liquid to ice, in situ primary ice nucleation, aerosol regeneration along cloud boundaries where you might have sublimation or evaporation. So it's a lot of complexity we try to deal with in the model as well. And then here I'm showing this famous or infamous image from Danny Rosenfeld's paper where he's looking at this concept of aerosol invigoration. We're not going to touch on that so much today, but I wanted to use this to demonstrate that in pristine conditions up top here in this panel, we see a developing cloud that tries to grow, it precipitates out, and kind of starts to get sheared apart in a clean, low aerosol environment. If you add aerosols to it, the idea is that you get continued condensation, it doesn't rain out as effectively, and it can grow and develop a lot more ice. So we're going to talk about what happens within the cloud, regardless of whether or not there's invigoration. So in terms of aerosol loading impacts, it's pretty well understood that in many cases, raindrop production is inhibited by aerosol loading by reducing collision coalescence growth of smaller droplets. And this permits more cloud droplets to be lofted to higher in the clouds, and they continue to grow by condensation. And this has been observed in many past papers. What is a little more unknown is that rhyming growth of ice via collection of liquid drops has been found to either increase in high aerosol environments or decrease. And it is really due to competing microphysical factors as well as environmental factors. And so we want to try to take a look at it, see what's happening to the ice and the rhyming growth and the clouds that we're simulating in the tracer campaign. Okay, so 2 questions I want to ask today. What microphysical similarities can we discern between the radar and the numerical simulations in a varied aerosol environment? And then what do simulations of isolated convection reveal regarding aerosol impacts on the distribution of ice and the ice microphysical processes going on in these clouds? Okay, so I want to mention, because we're looking at the simulations both from a radar simulator perspective as well as standalone, I want to take talk a little bit about the cases we're simulating. This is the domain we're using in the model. We're going to be focusing on grid 2 here in the Houston, Texas area. We're simulating at 250-meter horizontal spacing. So we're definitely in a convective resolving regime. We chose 6 different events that span the warm season of the Houston, Texas area. We chose these events based on the availability of observations as well as aerosols that we can use to initialize the model. At CSU, we're using the Regional Atmospheric Modeling System, or RAMS, that was originally developed at CSU starting in the 1980s with Bill Cotton, Roger Pilkey, and others. Each of these simulations was initialized with Era 5 reanalysis, was run for 24 hours, and most importantly, we're outputting data at 2-minute frequency, so we can actually track convective cells using a relatively new Python tool called TOBAC, or Tracking and Object-Based Analysis of Clouds. So we can really hone in on what's happening in the convective cells. There's a lot of information here, but this is to say that we used observations from an SNPS aerosol time series that was collected during tracer. We isolated the 10th percentile that we call low aerosol and the 90th percentile that we call high aerosol. And so for each case, we ran a low aerosol simulation and a high aerosol simulation to compare the change that we could potentially see in the extreme range of aerosols that were observed. And so we have a couple of low aerosol and high aerosol vertical profiles of aerosol concentration that we use to initialize the model. Now we have to do this horizontally homogeneous, so it is somewhat idealized, but we only had the aerosol instrumentation at one location. So it's kind of a somewhat idealized scenario in terms of representing the aerosols. But this is relatively clean and this is relatively polluted. So I'll usually refer to these as clean and polluted. And I do want to credit the folks at Brookhaven Lab for helping to provide the aerosol instrumentation, the data here, and then the groups at Texas A&M was able to provide us the aerosol profiles using a combination of LiDAR and radio sound measurements that they took during tracer. This just to give you a snapshot of some GOES imagery. It's somewhat washed out with the light in the background, but this is each case that we simulated at 5 p.m. local. So we can see that there's a lot of scattered cumuli in the area. Some become a little deeper and are able to precipitate heavier. But it's just kind of the nature of the convection that we see on typical afternoons in the Houston area. Galveston Bay is located right here. The CSAPR radar is somewhere down around here and can scan and observe a number of these cells. Here's an animation from one of these case days. This was June 17th. You can see the development of widespread cumulus across the domain. Some of them grow deeper and are more heavily precipitating. I'll let this run again. This kind of goes overnight here and it's going to start over again. You should be able to see a distinct sea breeze forming later in the day as we get a clearing of the marine due to the marine air coming onshore. So there's a complex interplay of urban and marine conditions happening in this environment. Okay, so first I want to take a look at what Mariko is finding from the CSAPR2 radar observations of convective cells, and then radar simulated convective cells from the model. So Mariko was able to take our model results, run them through the CRSim radar simulator that she developed, and so we can have some similar quantities to look at, because the model doesn't natively output radar reflectivity or ZDR and these sorts of quantities, but the radar simulator can ingest model data and output these similar quantities. So during the tracer IOP period, Mariko and others were able to track nearly 1,500 cells. Nearly 400 of those were classified as deep convective. And after a lot of experimentation, she was able to correlate some of the SMPS aerosol data nearby and separate this into a low aerosol regime and a high aerosol regime, with the caveat that the SMPS low and high conditions were representative of what the radar was seeing. It's not a perfect scenario of how to separate these, but we're finding that it's a relatively good delineation between cleaner and more polluted environments that the cells developed in. And so she ran composites of the low aerosol cells and the high aerosol cells that we can compare and contrast with one another. And then use the CRSim radar simulator on the model data I mentioned to also distinguish low aerosol and high aerosol environments that we can also make a comparison with. And then once those composites were created, she was able to do toe-back cell tracking on vertically innervated liquid so that we could really focus on what's happening over the cell lifetime. And this kind of offers a qualitative comparison between radar and simulator, looking at the similar types of radar-derived quantities. Okay, so we'll first take a look at the radar observations on the left. This is data model simulations on the right. So the left column is the different quantities from the low aerosol simulations and the high aerosol on the right. So we'll just kind of step through and get a main takeaway from each comparison. The top row here is reflectivity. So going from low to high aerosol, we generally have a little bit more ice phase reflectivity that's seen. We have a little bit more high ZDR in the high aerosol scenario, suggesting maybe we have more oblate droplets in that scenario. We tend to have larger D naught, where D naught is the median volume drop diameter, and we tend to have a bit lower number concentration. So we end up with fewer but larger raindrops in a more polluted scenario. And this has been seen multiple times in the literature as well. And in comparing the ice that we're going to be looking at, she tends to find more grapple in the high aerosol scenario. So we're going to really be focusing on the ice a little bit later on. So if we look at the model simulations, comparing clean to polluted, in the reflectivity, we tend to see a lot more, a bit more ice phase reflectivity, higher ZDR, a larger median volume droplet diameter, and a lower drop number. So while the magnitude change between clean and polluted is different, we still see the similar sorts of trends where we have fewer but larger raindrops being generated in the more polluted scenario. So we're glad that we see that the model producing roughly what the radar is seeing. And if we trust that and we feel a little bit confident in the model, we can start looking at other things that we cannot get out of radar observations alone. We can start looking into process rates and things like that we can pull out of the model. Okay, so we're going to look at next advanced model simulations of tracer events. So we did cell tracking with the model output at high temporal frequency. We used the toe-back tracking, and we tracked on mid-level updrafts. So we're not representing in this figures that follow the entire life cycle of the cells, but we're focusing on the period where there's reasonably strong updraft. And we did this at various threshold criteria. We're going to be looking at cell core composites. So the center of the cell is roughly within 4 kilometers radius of the identified updrafts of these cells. And we're going to be focusing on cells that last at least 24 minutes. So we're getting, doing our best to get a cycle of convection, not really short-lived cells. So on the top here, I've shown the distribution of low aerosol cells for each of the cases we're looking at. the cells that are tracked in the high aerosol scenarios. And just want to point out there's a different distribution of the number of cells. So each squiggle here is a cell identified in the tracking algorithm. So some days had a lot more convection than others. So we want to try to treat those equally. So we generated time height cell composites that are computed by taking each simulation composite and then generating a multi-event composite that weights each event equally in order to have a kind of fair comparison across different convective days. Okay, so we're first going to look at simulated aerosol impacts on hydrometeor characteristics in the tracked cells. Okay, so we're going to be looking at, for the next few slides, we're going to look at these time height cell composites of the normalized cell lifetime. So I want to orient you to what we're looking at here. So for each variable that we look at, this one is liquid mixing ratio within the cell core composites. So we're looking at this triplet of figure panels. These are altitude, and this is normalized cell lifetime. So 0 here is the beginning of the identified cell by updraft. And the 1.0 here signifies the end of the tracked cell, also tracking on updraft. So beginning and end of tracked cell. For each of these triplet figures we're looking at, we're going to have the low aerosol on the left, the high aerosol results in the middle, and then this is the difference field taken as high minus low or polluted minus clean. So for example, for liquid mixing ratio, when we go from low aerosol to high aerosol, we see more liquid water aloft, less liquid generated at the surface, meaning we're getting less rain, but we're sustaining more cloud water in the more polluted scenario. So that follows with what we would generally expect in an aerosol loading type of situation. So in terms of ice mixing ratio, over here on the left, our cell composites show the development of ice later on, peaking toward the end of the updraft period because it takes time to get the cloud forming, generate cloud water, generate some rainwater, and then as it deepens, you start to really get the surge of ice later in the cell lifetime. Now we see an increase in total ice going from the clean to polluted. And this is signified here with the red colors indicating an increase due to aerosol loading. So over the cell lifetime, and especially toward the end of the cell lifetime, we generate a lot more mass that stays in the cloud while we've got a sustaining updraft. So this tends to correlate with what Mariko was seeing in the radar observations as well. We saw more ice generated in the more polluted scenario. So there's good agreement. It helps us gain a little more confidence in what we're seeing in the model. Okay, so now we're going to take a look at more specific details of the cloud. So how are the changes in the total hydrometeor mass mixing ratio partitioned by hydrometeor type? Is the ice increased just in one hydrometeor type? Does it all sit in little cloud ice? Does some of it also increase in the hail and wetted hydrometeor category? So we'll take a look at that, and then look at the primary ice microphysical processes involved in these changes that we see in the hydrometeor distributions. Okay, so we'll first take a look at cloud water. Cloud water is the first hydrometeor species to respond to aerosol loading. You load the cloud with aerosols, you change the cloud droplet population, and then you get all of these other effects downstream. So first, we're going to take a look at cloud water mixing ratio, and then a droplet number concentration, and then droplet size. So what we see, and from going from clean to polluted, we have an increase in cloud water mixing ratio. So in general, we get a lot more cloud water generated aloft above cloud base, and as it grows deeper, we have a lot more cloud water over a deep depth, which fits with theory of adding aerosols in this type of environment. We also see a positive increase in cloud droplet number because we have a lot more aerosols, a lot more nucleation sites. So we have more cloud water, more cloud droplets, and we end up with a lot smaller cloud droplet size. So we've really changed the cloud droplet distribution by adding these pollution aerosols. So then how does this affect the development of rainwater in these convective simulations? So we see after the cloud begins to develop, after a little time has passed, the rainwater mixing ratio maxes out sort of during the middle of the cell lifetime above cloud base. And when we go from clean to polluted, we see a big reduction in the rain mixing ratio. And that's indicated here by the blues showing less rainwater. So we're not as efficiently creating rainwater in a more polluted scenario. We're suppressing rain formation. So what does this do to the rain droplet population? When we go from a lot of raindrops to a few raindrops. So we have a lot less droplet number, which we also saw from the radar analysis. But it turns out that we end up with a larger raindrop diameter. So we end up with fewer but larger raindrops, but overall less rainwater. So we've changed the rain droplet distribution. And this agrees with what we saw in the previous radar analysis of fewer but larger raindrops in a more polluted scenario. Okay, so if we take this modified droplet population and we allow some of that to be lofted up toward the cloud anvils, what do we see happening to the cloud ice? Where cloud ice is considered very small ice crystals, 15 microns to 100 microns or so. So if enough of these get lofted in the deep convection, we see this surge of ice crystal formation above 10 kilometers, which is about the homogeneous freezing level of -40°C. And when we go from clean to polluted, we see a lot more cloud ice being generated up toward the anvil levels of the clouds. And the number concentration also responds. We've lost this high volume of high number concentration cloud water, and we get a lot more number as well. So more cloud ice mass and more ice number. So we get a huge amount of droplets freezing at the upper levels of the clouds, and they're really tiny crystals. So there's the potential to really increase the lifetime of these cloud anvils. And I do want to also point out we have a bit more cloud ice happening down here, just above the freezing level. And we'll kind of come back to that, try to understand what's going on in this level as well. Okay, so once you've got cloud ice up in the anvil, you've increased the amount of ice, the ice number. As these sit around and they start to fall, they can undergo aggregation. So we represent aggregates in our model as well. And because we have a lot more cloud ice mass, a lot more cloud ice number, we end up with a lot more aggregate mass and aggregate number. And that's seen here going from clean to polluted or aggregate mass over a deep depth of the cloud. They'll form up here and kind of start to precipitate toward the lower levels. And we see a large amount of aggregate number as well. So we've increased mass in these more unrimed ice categories. So then what happens to the more wetted ice? Here we're going to look at hail, and hail in this model really looks more like wetted graupel. So we can almost put graupel and hail into the same categories here. Some models represent one or the other. We do represent both in RAMs, but in this situation, hail looks like really graupel-sized particles. But what we end up with in going from clean to polluted, we end up with more hail mass in this type of scenario. There's a lot more cloud water that can be rimed onto pre-existing ice crystals to end up generating a lot of hail mass or rimed or heavily wetted type of ice particles. And however, the hail number concentration tends to be less. So we have more hail, less number concentration of hail, which indicates that the hail tends to be a little bit bigger in these scenarios under the more polluted conditions. And we think that there's less hail number because we have less rain droplet number. Raindrops that get lofted above the freezing level can act as hail embryos and then grow by the riming process. So we think that the reduction in rain number has an impact on the hail number, but once it's lofted, it can undergo heavy riming and generate more total hail mass. So there's different processes impacting the different types of ice that we see in these deep convective clouds. Okay, so we've speculated on some of the microphysical processes involved. Let's take a look at some of these processes that we can pull out of the model diagnostics. Okay, so the first one we want to verify really is this cloud water to rain conversion, or the autoconversion and accretion process for creating warm rain. So what we see is a high rate of conversion in the clean scenario, a low rate in the polluted scenario. So in general, less autoconversion and accretion going on, and that tracks with the fact that we get less rain generated in the more polluted scenario. Now, if we take a look at cloud ice number nucleation, we see that this really peaks above 10 kilometers in both clean and polluted, but it is increased in more polluted scenario. So this is just validation that we're getting a large increase from homogeneous freezing at around the -40°C level, which is about 10 kilometers altitude in these simulations. So homogeneous freezing is a big dominant process in terms of new ice nucleation. it doesn't mean we don't have primary nucleation happening at lower altitudes. It just means because this convection is reaching that level, we just get a surge and it's dominating the ice nucleation signal. One other one that we can look at is the secondary ice production or the Hallett-Mossop process. And so what we see here is that because we have increased the cloud droplet number, we could have more collisions with ice particles that allow some splintering to happen. This is more one of the unknowns in the world of secondary ice production because there are different mechanisms. We simply represent the Hallett-Mossop process in the RAMS model, but we do get a surge of ice crystals being generated through this ice splintering mechanism. Could there be other mechanisms involved too? That's a possibility. We discussed a little ice nucleation earlier, and it's a difficult process to try to simulate. But we do see the surges of ice crystals, and this goes back to that I mentioned a few slides back, and we saw a little bit of ice increase at these lower altitudes, and we think that's because we're getting this secondary ice production generation because we modify the cloud droplet population. So that could be impacting the number of ice crystals we have at these warmer or lower altitudes. Okay, so a few more important processes going on here that we want to look at and tie back to the microphysics. The rhyming process is key here, especially for hail generation or gravel generation of these wetted particles. And we see it in this scenario that if we go from clean conditions to polluted conditions, we get this increase in rhyming over a fairly deep depth of the cloud, and especially where we see this increase in hail mass. A lot of that is going to be due to increased rhyming in this scenario. So at the very beginning, I said there are papers in the past that show a reduction in rhyming in an aerosol loading condition, and other papers that showed an increase in rhyming. So it really depends on what competing processes are going on, what environment you're in, and it just adds to a lot of the uncertainty that perhaps is what's reported in the IPCC reports. It really depends on conditions and these buffering of various processes. So we see increased rhyming of cloud water. However, we also have to consider raindrop rhyming that we see a decrease in because we have less rain being generated. However, the decrease in collection or rhyming of raindrops by ice is overcome by the increase in rhyming by cloud droplets. So the decrease in this is offset by the increase in this one, so that we see total freezing of liquid water going up in this scenario. However, if you change the distribution a little bit, this could be opposite. So it really depends on the distribution of liquid, the distribution of ice, and how those are relative to one another as to whether you see an increase or a decrease in rhyming. In this situation, and for these scenarios, and for this amount of aerosol loading, every case that we've looked at shows an increase in rhyming. So we see that in the composite here. And then final, just to note this is a net total melting in these three panels down here. And again, we go from clean to polluted. We do tend to see more melting occurring because we have more ice. There's more melting. And we think that this increased melting leads to this anomaly we see in the rhyming of rainwater toward the end of the cell lifetime. So there may be some recycling of rain that is generated from melting of ice, feeding back into that. That's going to take a little more digging to be sure of this. Okay, so the last of these plots, I believe, we're going to look at, is the rhyming by every ice category consistent or is it variable? So here we're looking at rhyme of cloud water by snow particles, by aggregates, by gravel, and by hail. And what we see is regardless of the ice species, we see an increase of rhyming due to the added pollution aerosols. That isn't necessarily always the case, but in this scenario, rhyming is a big drying process, increasing the ice mass in just about every category of ice that we represent in the model. Okay, so then what does this mean for latent heating in the column? So you increase condensation of the liquid phase by adding pollution aerosols, and you increase the amount of ice, which leads to the increase in rhyming. What does this do to the latent heating in the column? So what we see here is the latent heating over here, and the clean and the more polluted, and we see more heating or like heat release that gets deeper and deeper over time as we develop more and more ice. It peaks here, down here at the cloud level, because the latent heat of condensation is much greater than the latent heat of freezing. We do see the freezing contribution up here, but it's not maximized as much. However, because we have more latent heating in this scenario, it does generate more buoyancy. We have potential to invigorate the storm if the environmental conditions are right. And then if we take a look at latent cooling, we see an increase in latent cooling from clean to polluted. The greater cooling here is basically just an offset at cloud edges where you have entrainment getting in there because we have a population of smaller droplets. The population as a whole more readily evaporates at cloud edges. And so we get latent cooling from evaporation. But more importantly, we get less cooling at the surface because we have less rain being generated, even through melting of ice during this strong updraft phase. And this really does have implications for cold pools being generated for convection. So at least during this phase of the trapped convective cells, we may be generating weaker cold pools at the surface. These could precipitate out more heavily later on after the updraft has really decayed, but we're looking at mostly the updraft phase of the convection here. So there's lots of implications for how changing the liquid and ice in the cloud, how that impacts the latent heating, and how that impacts the persistence of the cloud as well as cold pools being generated. Okay, so this is the final slide. This is kind of my first stab at a conceptual model of what we're seeing in situations where we add aerosols to the convection. So these are a summary of the aerosol impacts. And I'll just offer a brief summary. So we have different levels here. We have the surface, cloud base, freezing level, and then the homogeneous freezing level. So initially we add aerosols. We have more cloud droplet mass and number. And this indicates a smaller size of cloud droplets. So some of these will undergo collision coalescence and produce rain, which primarily sits in the area of the black arrows here, the solid arrows. We get less raindrop mass and number, but a larger size of raindrop. And that change in the raindrop population can have impacts on whether or not we have more or less hail embryos that can get lofted and grow. So some of these, however, some of these droplets can make it up to the homogeneous freezing level up here above around 10 kilometers. This then freezes and increases the cloud ice mass and number. And we generate smaller ice particles that can last for a long time up at anvil level. However, some of them will undergo aggregation and begin to fall in the clouds. So we have more aggregate mass and number, kind of peaking in this altitude range. Once we develop ice in these mid-levels, either through lofting of some raindrops, settling of aggregates, we have this change in cloud riming rates. So we have more cloud riming and less rain riming. And the balance of these determines whether or not we have a total increase in riming or reduction. At the same time, we have more secondary ice production happening because we've changed the cloud droplet distribution. That can also impact the number and concentration of hail embryos in the mid-levels. But ultimately, the aerosol loading generated more hail mass, but less hail number. And that can have implications for how much of that potentially reaches the surface or not. So just to summarize, it's a complex interplay of what goes on within all of these different competing processes. So I hope I haven't overwhelmed you with all of these processes, but the main takeaways here are that if you change the aerosols, change the cloud droplet distribution of the population, that has impacts for both the rain categories, the rain liquid category and what reaches the surface, as well as how much ice is generated and is sustained up at the anvil levels. This can have a cloud lifetime effect as well. If the anvils stick around and reflect more radiation, that has implications for that as well. And we saw that this can change the surface precipitation, and that has implication for convective cold pools as well. So I'll leave that up there as my conclusions, and I'm happy to take any questions.
Thank you for nice presentation, and we have a plenty of time for questions.
Yeah, that's I still got just to clarify, so for each of the days you ran two cases polluted and clean for each date, right?
Yes, yes. Yeah, we ran, for the model simulations, we ran clean and polluted for each date and generated composites of all of those days.
And I guess just follow up on that question, like how much variability you see between clean and polluted cases across the different days? Is this more a consistent story across different days, or are there substantial daily variabilities?
So I did look at the individual days, and for most of these fields that I showed here, it was relatively consistent. There might be one outlier here, one outlier there. For the most part, things were consistent across the different days, in spite of it spanning from June to September. But we saw similar types of convection on the different days. So it seems like the aerosols had similar effect. The magnitudes were different. And I think that when we looked at, when we started looking at some of the composites, if there was more variability from day to day, we would start seeing more situations where you have mixing here of blues and reds, indicating plus or minus. But for a lot of these variables, it was pretty consistent, but with changes in magnitude. The trends were roughly the same. Yes, Brian.
Similar question, but just curious about that variability. I mean, what is different in those cases between a case that had more of a signal or more stronger amplitude versus another? Is it something in the environment that's different, or some other factor?
The answer is I don't know yet. There's so much to look through. So I don't know the answer to that. The environmental conditions, I think we'll learn more about that from the tracer model intercomparison project that we're doing, because we're going to have more models on board. And we can see how consistent things are. We'll see if WRF with different versions of the microphysics see the same sorts of trends, or if there's more day-to-day variability. I think that'll give us more of an answer than what I have right now. Yes.
Yes, a very nice study. I really like it. I have a question, of course, the nitty-gritty details is the aerosol. And so you polluted and clean scenario. It seems you focus mostly on the numbers. My question would be, what are these aerosol types, or what kind of hygroscopicity did you assume? And it seems they all activate as cloud droplets. They have homogeneous freezing. But if you have some insoluble particles or mineral dust in it, could have freezing between the homogeneous and the freezing line. So how did you initialize this activation? What kind of kappa or IMP values did you?
Yeah, so we had to make some assumptions.
Yeah, of course.
But the sizes were, so we did have sizes from the SMPS
Yes,
to go on.
Yeah.
The
Size and number.
the kappa. It's all the way back. Okay. So we did have Maria Zawodowicz at Brookhaven was doing a lot of the aerosol speciation work. So I didn't really highlight this here, but here's the kappa that she derived from. You can't see the numbers here, but this is the entire tracer field project period. And so we really took the 50th percentile of the full campaign time series and used the kappa here of 0.26. So relatively soluble. And so for most of because we designed a lot of this for the tracer intercomparison project, we kind of had to assume a certain chemistry. So for this model, for RAMs, we chose ammonium sulfate. There is a lot of ammonium sulfate in the area. It's not always the dominant chemistry, but it's pretty prolific. And so that's kind of what we used, a reasonable kappa based on observations, and then an ammonium sulfate type of particle.
If I may just follow up on that. So I'm not surprised you get more homogeneous freezing in the polluted case if you have such type of aerosol establishment, because you have more droplets when they freeze.
Right.
It would be interesting. We discussed a little bit the secondary ice processes. That's exactly the level where you would expect it to happen. But it would be interesting if there's also some primary going on in this level, if you would throw in some mineral dust
Right.
or sea spray aerosol, which could also act as an IMP, and just to refine it a little bit more.
Yeah. So we did the models that can handle this, and we do represent separate category of IMP for the model, and I think we based it off of some of the MC3E observations of IMP representing roughly a continental scenario, and use that as our background IMP, and then use the DeMott formula to activate those. Maybe it's not the best,
No.
but it's
I don't know. Which is
yeah, it's what we've got right now. So we did have background IMP to allow primary nucleation to happen at the warmer temperatures. It would be interesting. There were cases from Tracer where there was observed Saharan dust. I find it unusual for it to make it as far as Texas coast.
Yeah, that's.
I've seen it in crystal phase data over Florida,
Oh yes.
but there were some dust days. But I don't think that was dominant compared to the urban aerosols, but it was still there, and perhaps it influenced things through ice activation.
I just have one 10-second question.
Yeah.
Your composites, you showed altitude and then your y-axis. In the next slides, you showed all this pattern.
Which one?
Yeah, the analysis. Which
Okay.
you showed this multiple. Yeah. No. These guys. Yeah.
Yeah.
Do you have that as a function, the temperature profile and humidity available from your model?
Yeah.
To see what was supersaturation or temperature at the different altitudes? Then one could, in the observation, but also in the model, think about IMPs and CCN.
Yeah.
That would be very helpful.
Yeah, we could certainly do that on a temperature
that
scale.
was just
Yeah.
like-
That would help us narrow it down. Otherwise,
Yeah.
I've looked at individual profiles to guess where the various freezing levels are.
Yeah, I don't know what the temperature there is.
Yeah.
So I cannot think microphysical.
Yeah, freezing level in these, most of the cases, it varies a little bit, but around just under 5 kilometers or so.
Yeah, makes sense.
Yeah, to have again, like I like those animations of actual clouds, but there, what I kind of find it interesting, like when you see the sea breeze, shallow convection disappears, and then it's supposed to be like marine air, very humid, warm. Why it gets rid of shallow convection? Have you looked at your model? Does it reproduce this result?
The model does produce,
But does it get rid of shallow convection at the coast?
it does, yes. We do see the sea breeze front. It'd be nice to objectively analyze this. It can be difficult. Different people in our group have tried different algorithms to try to track the sea breeze. And it's challenging depending on whether you do it by change of moisture, change in temperature, change in winds. But RAMS does do a pretty good job picking up the sea breeze, and it'll kind of clear out convection. See if this starts over. It'll start clearing out convection as it moves on shore and clear this out just because it's a little more stable. So we do see that pretty consistently. I don't think it produces as widespread of little cumuli. We may not be at high enough resolution to really pick up the little tiny clouds all over the place. But I think in some of the high resolution runs that others in our group are doing, they're able to pick up some of these tiny little cumuli around. But the sea breeze front is observable even at lower resolution simulations. Yeah.
Yeah, I have a question. Really interesting work. Did you consider like whether or not the direction that the systems were moving kind of impact, like if you started with a system over the Gulf of Mexico, I'm assuming there's different aerosols as opposed to if it starts over continental. Did you do any comparing and contrasting as like a maritime air mass started to move over the continent or vice versa?
That is something we thought about doing and haven't done yet. So we discussed this for the Tracer model intercomparison project too, where we were thinking, okay, so maybe along the coast, anything over the ocean, we initialize with a more marine type aerosol profile, and everything over the land doing more with the urban type aerosol. We haven't done that yet. We do suspect it would at least impact some of the convection that forms along the sea breeze at the intersection of an aerosol boundary, but that's still work in progress.
Any question?
Yes.
Steve, so this big working group came up with this idea to study, use Houston to study aerosol convection interactions, a lot of modeling work. You had one slide of observations. You work with a very good observationalist that now has to convert your model to radar and etc. But the bulk of your work, it's all diagnosed from the model output. So what next for observations? Because any of these numerous slides can be benchmarked against observations. Mariko is an expert. Any of these process rates, when you actually do it in the simulator, makes a difference in any observing signals of the radar. Or we should just rely on the model for now. What do you think?
I agree, there's more that can be done, and I can show more from observations that Mariko has been working on. And there, I know somebody that works with GWIN on the tracer and comparison project has started digging more into some of the observations compared to the models, including some of the boundary layer stuff that Katya has done. So there's other comparisons we can do there. So the plan is to certainly add more of that into the analysis.
Yeah, actually, I'm not satisfied with the tracer data set yet. I need more, more data here actually. Because there's only 100 for each scenarios. And then we didn't get the CCN observation from tracer. Yeah, unfortunately. So I want to again do the same things if possible. Yeah. Any question? Actually, I have a question. Your aerosol condition is the initial conditions, and then does this situation continue entire simulation, or the aerosol were consumed by the precipitation or clouds?
Yeah, the aerosols are consumed. So all of these aerosol processes are represented in our model. So we do have nucleation scavenging. We do have precipitation scavenging. Aerosols can be, aerosol mass once in a hydrometeor can be transferred to other hydrometeor species through collision coalescence. And then we also have regeneration of aerosols. So we fully track all of these things as best we can in a bulk model. So they can be consumed, areas can be cleaned out, regeneration can restore aerosols back to the field. So it could be that some aerosols, if an area is cleared out by one convective cell and another cell develops, that one particular cell could have less aerosols because it's been washed out from a previous area. So what we're seeing with the tracked aerosols is kind of the mean of all of that. But there's the way we initialize it, there's so much aerosol in there that it's unlikely that these little convective cells clean out a large area over time. But we do see that happening and try to represent all these various aerosol processes. Other models that were involved in the ACPC that I mentioned, some of those keep it static the whole time. So if you initialize with a profile, it stays there. So I feel like we are ahead of the curve with a lot of bulk models. This may not be as complete as, say, a WRF-Chem type of model that represents way more aerosol processes, but for a bulk model, we managed to represent a lot of that. Yes.
I see that you mentioned that the process rates depend on this interplay of ice versus liquid mass and concentration. So it depends on environmental factors. So what are these primary environmental factors which can contribute to this balance? And I see that there's only one pattern that is shown in most of the data that you've shown here.
Yeah, so depending on, well, all of these cases show similar, like was mentioned, all the cases show similar trends. But if one cloud is potentially more unstable than the other, there could be some variation in the supersaturation that's generated. So if one case or one cell has greater supersaturation, that can determine potentially how much condensation there is. And then if you change the condensation rate because there's more supersaturation, then maybe you get more cloud droplets lofted to the freezing level. So you change some of those conditions. If the temperature is slightly different or the saturation is slightly different, then it can change the ratios of which processes are dominant in these sorts of scenarios. Is that what you mean?
Yeah, so I mean, I was just trying to relate back to what supersaturation in fact goes back to? Is it more like dynamics? You have draft peaks, mid-level moisture, entrainment rates, things like this.
Yeah, definitely, because we're gonna have a range of cells of different depth. So some of them are going to have, some of them are gonna barely meet the updraft threshold of 3 meters per second. Others will have 10, 15 meter per second updrafts. So the different cells will have different ratios, I guess, of which processes are dominant. So what I'm showing here really is the mean of all of those that are developed and tracked. But there definitely is variability, which could explain some of the case by case variability that we see. Even though the trend is similar, the magnitudes are different from case to case.
Questions? Okay, let's thank you, speaker.